Second type we're going to look at today is similar triangles. This is kind of interesting because it's sort of something you're supposed to learn in grade 10, but a lot of us probably didn't. But it's simple, but you're going to learn about it now. You've seen it before when we do special triangles in trigonometry. Trigonometry is similar triangles, is the same thing, but there's a whole other kind of question that you can solve with what we call in education similar triangles, like it's a thing. It's fairly simple. And it almost always has to do with spotlights, or lamp posts of some kind. So you can usually spot these pretty easily because it has something to do with light, although trigonometry questions can also have to do with a light source. So there is some crossover. And a lot of the questions we've looked at have to do with triangles. I mean, the other one was a triangular trough. This one's triangles. Substitution ones can be triangles. We see triangles, like Pythagorean theorem is triangles. Trigonometry is triangles. So there's a lot of triangles in these. So you can get them mixed up. But these ones often are lamp posts or spotlights. And somebody walking towards or away the light source is usually how these ones work. So that's how you can spot it. So a man who is 1.8 meters tall walks away from a street light that is 5 meters high. If he walks at a rate of 1.3 meters per second, how fast is his shadow growing when he is 8 meters from the base of the light? So one thing that's going to be really important is we're going to have to draw this and label it, and that's going to help us think about it. So another thing, and along the way, you'll notice we really have to think about, like, what direction is he walking? So what is growing? What is shrinking? It's going to tell us some of that, but we're going to have to really think about some of the other parts of that. So keep that in mind. So I'm going to draw a triangle here. It's a right triangle because the lamppost is straight up. And I'm going to draw the 1.8 meter tall man. He's walking away from a street light, so he's going this way. So I've got a little demo here that can help us visualize this. If you're close to the street light, your shadow is going to be short. There's the shadow. This is the person. This person, I can make him 1.8 meters. There we go. Okay. So the shadow is not very tall, and that makes sense. If you're very close to the light source, it's above you, your shadow is going to be short. Watch what happens is this person walks away. So what is changing? Which ones are we given? What are we finding? This is the shadow. We can see that it's increasing. It tells us it's increasing, and the question may or may not. It might say, how is the length of a shadow changing? And you have to figure out if it's increasing or decreasing. But I got to know this is the shadow. It's increasing. That's what I'm trying to find. What is this? The distance from the lamppost, which is also increasing. And like, what is that in the question? So there's lots of things going on here that you have to be able to think of. And there are different types. We're going to look at one type that's quite different, and if we have time, a third one that's similar to this but different a little bit. But there are other types that are differenter. So you got to be able to visualize this and think it through. Okay, let's start labeling some stuff here. Anything that's changing needs a variable. So the shadow is changing, so I'm going to call that y. We don't yet know that that is. We might be able to find it. Let's wait and see about that. This length is changing because this is the distance the person is from the lamppost, and they're walking away from it. So we have to call that x. We know what it is. What is it? 8. And we know what else about it? So, right, so that's this distance, the change in this distance, right? It's not the change in this distance, it's the change in this distance. So that's dx by dt. And is it positive or negative? He's walking away from the street light, so this distance of 8 is growing, so it's positive 1.3 meters per second. What else do I know? There's one more thing that I'm missing. Seema? Yeah, good. This person's height is well, is it? People grow or shrink. The lamppost is definitely constant. The person's height might be changing, but probably way too slowly for it to be relevant to the question. If they were walking up a ramp, this question trickier, that would make it harder. But fortunately, we don't have to take that into consideration. X is changing, Y is changing. We got two variables changing. This is constant, so we don't have to worry about it. This is constant, so we don't have to worry about that. But what's the relationship? What's the equation that relates all of these values? I'm going to redraw the triangles. This is a really good trick when you're doing these kinds of things, to redraw the triangles and relabel them. You may or may not have to. Once you've done it a few times, you may not have to, but it helps to do it at first, I would say. So we're going to redraw the triangles, and then we use similar triangles to come up with our formula. So I've got two triangles here. Whoops. One is small. One is bigger. And what makes them similar? What are similar triangles? Similar triangles are two triangles whose lengths are in proportion to each other. So if I double this length, I double this length. If it has double the base, it has double the height, like special triangles in trigonometry, right? They're in the ratio of 1, 1, root 2, or 1, 2, root 3. But all triangles that have equal angles are similar to each other in the same way, where they're proportional. I don't have to find the angles. I could, but I don't have to. But like, I know that this angle and this angle are equal. How do I know that? Well, because both triangles share this angle, right? The big triangle and the small triangle both have that as that angle. They both have a right angle, because this is also a right angle, assuming the person's standing up straight. So the third angle has to be the same. If the first two are the same, the third has to be the same. So they have three equal angles, so their sides are proportion. If I double this one to get that, I double this one to get that. That's what similar triangles means. It's not double because it's 1.8 to 5, but that's the idea. And all we do is set up a proportion. Is everybody okay with that? I do want to try to get to the other two, so I want to go through this quickly. So what's my proportion going to look like? It's going to look something like this. There's two ways that I could do it. I could do 5 over 1.8. And if I started with the big, I forgot to relabel these, so I'm going to do that quickly because we're missing something that we need. So this is y. What is this? X plus y. Not x plus y, right? So if I did 5 over 1.8, I started with the bigger triangle on top. I have to do the bigger triangle on top again. Or you could do a ratio within a triangle. It all works out the same, so it doesn't matter which way you do it. If I do 5 over x plus y, so the height over the length, then I do, again, height over length. You just got to be consistent in how you set up each fraction. But I think that's pretty simple and straightforward, isn't it? So you didn't do anything like this in grade 10? No. So there you go. Easy enough. Then I don't want to do quotient rule, so we're going to simplify this. So it doesn't matter which one we choose. I'll bring the y over. 5y equals 1.8 times x plus y. So I'm going to distribute the 1.8 and bring the y's together. Why not, right? It's going to make my life easier. So this becomes 3.2y equals 1.8x. And it's a super easy derivative again. If you wanted to, you could move the 3.2 to the other side and only have one number. It's up to you. So what happens when I take this derivative? Something curious happens. In fact, I'm not sure we wrote this out. We're finding dy by dt, right? The rate of change of the shadow. That's the shadow. That's what we're finding. What was kind of interesting that happened when we took the derivative here? And not with respect to? There's no x or y in the equation. So the actual length or the actual distance turns out is irrelevant. We didn't solve for y. We didn't need to solve for y, it turns out. We're finding dy by dt. dx by dt is 1.3. So 3.2 dy by dt equals 1.8 times 1.3. And that works out to approximately 0.73 meters per second. We knew it was increasing. The math confirmed that, so that all fits. Any questions about that one? Quite different from any of the other ones that we've done so far. It's a right triangle. If you thought Pythagorean theorem was how you're going to solve it, I mean, that's not going to work at all. So you have to know that which type is which type. The first thing is that you're using the right form on the question that you're solving. Spotlight on the ground. So this one's quite different. Spotlight on the ground, shines on a wall 10 meters away. So the other one was a lamp post. The light was up at the top. This one, the lamp is on the bottom, or the spotlight is on the bottom. A 2-meter tall man walks from the spotlight towards a wall at a particular speed. So let's draw this. So the person is 2 meters tall. The spotlight is 10 meters away from the wall. All right. What's different about this one, though? So in the first one, let's take a look. See how this is changing, the shadow length, and this is changing, the distance the person is from the lamp post. But what's also changing is the distance from the tip of the shadow to the light source, the bottom of the light source. Like that whole distance is changing. That is not true in this situation, because in this situation, it's 10 meters, the lamp post is 10 meters from the wall, and that doesn't change. So what's the other thing that's changing? As you get closer to the wall, your shadow is decreasing in size. See how important the visual is. So if I start far away, my shadow is quite tall. As I get closer to the wall, and that makes sense. You're standing in front of a light source, you're going to block the whole thing if you're close enough. As I get closer to the wall, the shadow basically approaches the height of the person. Does that make sense? So what's changing, I have to give a variable to. So we'll call this h. How fast is the shadow on the wall decreasing in height? So we are finding dh by dt. Could we find h? Possibly. We saw in the last example, we didn't need those lengths. So let's not bother until we find out if we need it. This one works out a little bit differently, but that part of this whole thing tends to be the same. We probably won't have to find h. Any questions so far? The only other trick to this one, and I mean, I think this is maybe a matter of memorizing, practicing a few times to remember this. This distance is changing. The total distance isn't changing, but this distance is, and this distance is. And they're changing at the same speed. Because as the person walks 1.2 meters towards the wall, meters per second, they're walking 1.2 meters per second away from the light source. So they're both changing at the same speeds. I'm going to call this one x. You could call the other one y, I guess, if you wanted actually. Actually, let's do that. We'll call it y. 3 meters away from the wall, so my scale here is pretty bad. If this one is 3 meters, then this one is 7 meters. So what is dx by dt? And what is dy by dt? What do you think, Daniel?
dy by dt is negative 1.2 seconds.
Nice. So this distance is getting smaller. This distance is getting bigger. If you give them both variables, like this one's 10 minus x, or this one's 10 minus y. If you give them both variables, though, you don't have to think about how it's going to work out. You'll be able to sub in and solve when we do the when we get our similar triangles part done. So again, I'm going to redraw these this time. You don't have to redraw them every time, but it, like I said before, it can be very helpful. So look at what happens. I've got x here, which again is 7. And this is 2 meters. And this is h that we're trying to find. And what is this? X plus y, but I don't want to do that, do I? What is this? 10. Right? Because it's not changing. Why would I call it x plus y? So it turns out I didn't need this part. But if you forget where, so I only needed to put an x here. But if you forget where to put the x, you could do both, and then it'll work out the way it works out. If I put the x here and called this 10 minus x, then I'd have 10 minus x here, and it would just be a little bit messier to do the derivative and stuff, but not that much. Okay, so let's do this quickly. So I've got h over 10. So I started with the height over 10 equals 2 over x. If I bring the x over, I have product rule. I don't want to do that. So instead, I'm going to change this to 20x to the negative 1 and take the derivative like that. Okay, very quickly. Uh, 1.2. So in this case, I did require one of the side lengths. That did matter. But I didn't need to solve for the height, or I didn't need anything else. Works out to about negative 0.49. Therefore, the height of the shadow is decreasing at 0.49 meters per second. Again, I'll repeat this. You have to interpret that as a positive value in your therefore statement and say that it's decreasing when it comes out to be negative. We knew it was going to be that. The question told us it was going to be decreasing. But anyway. Say again? It should be negative 2, yes, thanks. That's why it's over 7 squared. Yeah. Any other questions? We only got 7 minutes, but I think we can get the next one done. It's similar to the first one we did in similar triangles. We'll do it quickly. It's about a raccoon. So the raccoon is scrambling towards a street light and walking away from the street light, so that's why this question is slightly different. If the street light is 4 meters above ground, how fast is the raccoon's shadow decreasing in height when it is 3 meters from the pole? Okay, so the pole is 4 meters. The raccoon is 3 meters away, so that's somewhere around here. So one more time here. In this case, I am walking. In the first case, they started close and they walked away. So the shadow was increasing. In this case, the raccoon is walking towards. So look how its shadow is decreasing. And everything's changing. This is changing, and this is changing, and this whole length is changing. So we need an X and a Y. And this was the one where we already realized that we don't actually need to know the values of X and Y, do we? That's how the first one worked out, at least. So what is the last thing that's different about this one? How fast is the raccoon's shadow decreasing in height? That doesn't really make it, well, height from his feet, I guess, but length. So I'm finding what? Dx by dt when y is 3, but it turns out that might not matter. But I'm given dy by dt, and it is? What do you think? Something important here. Yep, what do you think? It's going to be negative because this is getting smaller because this person is going, or the raccoon is going that direction. So let's see. I've got 4 over x plus y. So I did height over length equals height over length, 0.4 over x. And the derivative couldn't be easier. Therefore, the shadow blah, blah, blah is shrinking or decreasing. Blah, blah, blah.